In this video, we'll be looking at using the Hungarian algorithm to allocate we've got three vehicles to three customers. And in this case, we need to use the Hungarian algorithm to allocate where the number of lines, covering lines, equals the number of rows of the matrix the first time. So we've got our Hungarian algorithm process here on the right. Obviously, you wouldn't have this in an exam. It's just to highlight each step. This Hungarian algorithm process should become innate. So you should practice this enough times to know this off the top of your head. Reason being is this can quite well pop up in the non-calc part of your exam. So off we go. Let's look at the context of the question. We've got a rideshare company. They have three vehicles, A, B, and C, and available, and three customers, 1, 2, and 3. They've all asked for a vehicle. Now A is 26 kilometers from customer 1. A is 17 kilometers away from customer 2, etc. This table here shows how far away every taxi is to every customer. Now, what we need to do is to match the tasks of the vehicles to minimize the total distance and find this distance in total. So the Hungarian algorithm helps us allocate when every resource can go to every allocation. Okay, so what we need to do firstly is go through a Hungarian algorithm and just double check, are we minimizing or maximizing? We can see here we're minimizing, therefore we don't need to invert the matrix or anything like that. Is there any dummy rows? No. No, the number of rows equals the number of columns, therefore we don't need a dummy row. So straight into it. Step 1, subtract the smallest entry in each row from all the entries in this row. So let's look at each row. What's the smallest value in this row? We've got 9. So I write a 9 here for my working. You can circle it as well if you like. Minimum here is 13. And the minimum here is 11. The next step is to subtract the smallest entry in each row from all entries in the row. So below we draw an appropriately sized matrix. In this case it's 3 by 3. 26 minus 9 is 17. 17 minus 9 is 8. And 9 minus 9 is 0. Now this process, subtracting rows and columns, helps us gather more zeros. 0 is important because they help us assign. Okay, we'll do this again. 15 minus 3, 13 minus 3, 15 minus 13, 13 minus 13, 17 minus 13. The last row we're minusing by the minimum, which is 11. So this becomes 250. Now we can say we've completed step 1. Step 2, subtract smallest entry in each column from all entries in its column. So what's the smallest value in that column? It's 2. What's the smallest in these? Well, we can see these are zeros. So what we're going to do is redraw our matrix, and we're going to subtract 2 from these column values and 0 from this and 0 from this. So 17 minus 2 and there we go. We've got our new row and column reduced matrix. So we've completed step 2. Now step 3 says draw straight lines through the rows and columns so that all 0 entries are covered. Now we need to make sure we cover using a minimum number of lines first. How I approach this is I go, okay, I can either put a line on a column, a row, or a column. So this line, how can it cover the most zeros at once? Well, I can put it here, that'll cover 2, here, that'll cover 2, here, that'll cover 2, or here. That will also cover 2 zeros. So it doesn't really matter. I'm going to put it here. Now these zeros are essentially covered up or disappeared. So now we need to use another line to cover the rest of the zeros. Well, we've got this one here, or this one here. So I'm going to draw it there. I've covered another 2. Now the only 0 we can see left is here. Now we can draw this as a column or a row, it doesn't matter. And there we go. We have just drawn our lines in. So because we've covered all the zeros. So ensure the minimum number of lines are used. We've done step 3. Step 4 says if the minimum number of covering lines is equal to the number of rows. Let's have a look at that. Does the number of lines equal the number of rows? Let's have a look. Well, the number of lines is 3. The number of rows is 3. So it does. So, if the minimum number of covering lines is equal to the number of rows, go to step 6. So we can go to step 6 now. And we skip step 5 in this case. So step 6 says, select and circle a 0 entry in each column of the matrix so that no other circled 0 entries are in the row. So let's have a look. Well, 0 reflects the best allocation. We only circle zeros. A looks like it's best allocated to 3 because there's only 1 0 in this row. So we circle that. Now, once taxi A is going to customer 3, customer 3 is used up and taxi A is used up. They're both allocated. So that means we can't use taxi A anymore, and customer 3 has already been allocated, so we ignore that 0. So customer 1 has this option here or this option here. Taxi C has this option here or this option here. Taxi C cannot be allocated to the 0 anymore, so therefore it has to go to this one. What's left? We've got taxi B's left and customer 2's left, and there's a 0 there. So now we've allocated, in a sense, by using our circles. Now, let's reflect this up here. Taxi C is going to person 1. We've got taxi B going to person 2, and taxi A is going to person 3. Now, the working I prefer to see for this, and we're running a little bit out of room, so I'm just going to move to green, but please write this underneath. You've got your allocations A, B, and C, and where are these taxis going? Well, A is going to customer 3, B is going to customer 2, and C is going to customer 1. And then I put down the time required. So A takes 9 minutes. Okay. B takes 13. And C takes 13. So what's the total time? Well, this becomes 26:35. So the total time, apologies, kilometres, because these are distances, aren't they? Total distance is, and we say 9:35 kilometres. And this is our example completed now for using the Hungarian algorithm where number of lines equals the rows of the matrix the first time. In the next example, we'll look at whether the number of lines doesn't equal the number of rows of the matrix the first time.